So, good afternoon, and thank you for the introduction, and thank you also for attending my talk. I am Andrea Rosà from Università della Svizzera Italiana, from Lugano, Switzerland. Today I would like to present our work titled P3, or a profiler suite for parallel applications on the Java virtual machine. This is a joint work done with Walter Binder, also from Università della Svizzera Italiana. And this work was originally accepted for publication at A+ 2020. Concurrency is becoming increasingly important to speed up applications. And for this reason, it is also fundamental to analyze concurrency and synchronization constructs used by concurrent applications. Doing so enables performance assessment and also detection of optimization opportunities. For this reason, in our work, we introduced P3, which is a novel profiling suite for parallel applications running on the Java virtual machine. P3 focuses on metrics related to parallelism, concurrency, and synchronization. And in particular, it can profile the use of concurrent entities, for example, threads, tasks, actors, and futures. It can also profile constructs and classes to implement synchronization, for example, locks, thread parking, and also synchronizers from the java.util.concurrent package. It also focuses on lock-free operations, and in particular, atomic variables and accesses to volatile fields. And finally, it profiles also the use of synchronized and concurrent collections. At the moment, the tool can be also readily applied to popular benchmark suites for the JVM and also to public code repositories, thus facilitating large-scale analysis in the wild. P3 only incurs a moderate profiling overhead, and the main challenges in developing the suite lie in achieving a moderate overhead, thus also reducing the measurement perturbation, and for this reason, also obtain a high profiling accuracy. To do so, P3 relies on the use of lock-free data structure. It also relies on an efficient instrumentation logic that inserts only few computations in the instrumentation code. And it also makes use of reification of reflective information in a separate instrumentation process. The rest of the talk is organized as follows. I will first present the metrics that can be collected by P3. Later, I will describe the main architecture. Then I would like to talk about the main implementation details of P3. And later, I will also talk about how P3 was used in previous research work. I will present the evaluation of P-cube that has been conducted on the Renesas benchmark suite. And finally, I would like to give my concluding remarks. Regarding metric collections, the collection of metrics in P3 is organized into modules that can be enabled and disabled individually. Each module contains or allows the profiling of multiple metrics, as you can see here in the slide. We have 4 modules that focus in particular on the use, the creation, and the execution of concurrent entities. In particular, threads, thread start and termination, tasks that are defined here as instances of runnable, callable, and fork-join tasks, the use of akka actors, and also futures and promises from the Java, Scala, and the Twitter libraries. An additional set of modules focus on synchronization, in particular the acquisition of implicit and explicit locks, the use of the wait notify pattern, thread joining, thread parking, and also synchronizers like semaphores, latches, and barriers. Another set of modules focuses on lock-free operations, in particular low-level operations like compare and swap, the use of atomic classes like atomic int, atomic long, atomic references, and finally, accesses to volatile fields. And the last two set of modules focus instead on the use of synchronized and concurrent collections that are frequently used by concurrent applications on the Java virtual machine. In addition to the metric that I presented before, P3 can also profile useful supporting metric and context information. First of all, P3 can profile the bytecode count, which is defined as the number of bytecode instructions executed by an application. This metric allows to normalize the other collected metrics with respect to a platform-independent quantity that can represent the amount of computations performed by the application. And this can be useful when comparing metrics collected in different applications with respect to a quantity that can represent the amount of code, the amount of computations executed. In addition, P3 can profile the caller context, which is defined as the method in which an event occurs. This information allows to profile the counters per method, and in turn, having the counters per method enables the detection of code where most of the events of a given type occur. And this can be a very useful information when locating optimization opportunities. Regarding the architecture, P3 is organized in a three-component architecture that you can see in the slide. P3 instruments classes at load time, and in particular, the instrumentation occurs in a separate process that is called the instrumentation server. When a class is loaded in the target application, the class is intercepted by a native agent that is attached to the target application, and this agent sends the class that was just loaded to the instrumentation server. Here in the server, the instrumentation logic determines which methods of the class that has been just received should be instrumented, and then it instructs the weaver to perform the instrumentation. After the instrumentation, the potentially instrumented class is sent back to the target application where the class will be linked to the memory of the JVM. When an event of interest occurs, the event is registered into thread local counters in the memory of the target application. And upon the termination of a thread, these counters are fetched and are sent to another component of P3 that is called the analysis server. In the analysis server, one component called the counter processor takes care of storing the events into appropriate analysis data structures. And these data structures will be elaborated when the running application terminates. And in particular, the trace handler will produce concise and readable traces containing all the events that were collected at runtime. In addition, Pcube also integrates plugins that can interface with popular benchmark suites for the Java virtual machine. These plugins, in particular, allow determining when the iteration of a benchmark starts and ends. And this is particularly useful for enabling the collection of per-iteration metrics. For example, this can also be used to differentiate the warm-up from the steady-state performance. At the moment, P3 includes plugins for the Renaissance, the Capo, ScalaBench, and SpecJVM 2008 benchmark suites, and users can implement other plugins for other benchmark suites. In addition, P3 can also interface with NEB, which is a framework for conducting dynamic analysis on public code repositories like GitHub, and in this way, P3 can be readily applied to conduct large-scale analysis in the wild. Regarding the main implementation details of the profiling suite, our tool is built on top of the Diesel framework for bytecode instrumentation. In particular, Diesel guarantees complete bytecode coverage, which means that every method with a bytecode representation can be instrumented, including also the ones of classes defined in the Java class library, which is notoriously hard to instrument. The implementation has been designed to keep the profiling overhead moderate while not jeopardizing the accuracy. In particular, the events are registered into thread local primitive counters where no synchronization is used. And this means that the instrumentation code is cheap to be executed. And moreover, we also avoid to allocate extra memory in the heap of the target application. Moreover, the costly elaboration of the counters is done in a separate process when the application terminates to reduce the profiling overhead and also to reduce as much as possible any possible measurement perturbation. P3 often requires to access reflective information on the class under instrumentation. Unfortunately, this kind of information is usually not available in frameworks performing the instrumentation in a separate process like Diesel. And in turn, this results in expensive solutions usually used in the instrumentation code. For example, the insertion of expensive runtime checks or the use of the Java reflection API in the instrumentation code. And they are both known to greatly increase the profiling overhead. P3 can instead access the reflective information thanks to the use of the Diesel reflection API, which provides partial reflective information on the class under instrumentation. And in the practice, making use of this API greatly helps in reducing the profiling overhead. For example, for one module that is called volatile, the original profiling overhead without using this API was very high, was above a factor of 1,600, but using the Diesel reflection API and adding access to reflective information in the instrumentation server, this overhead could be reduced to just a factor of 1.03. P3 has been extensively used by researchers in both academia and industry. And in particular, it was very important during the development of renaissance, which is a modern benchmark suite composed of 25 benchmarks that focuses in particular on aspects related to parallelism, concurrency, and synchronization. During the development of renaissance in particular, P3 was used to select candidate workloads for the suite, searching for them in public software repositories. And the selection criteria for these workloads was that they should show a high degree of concurrency and synchronization. And some of them were later included in renaissance. P3 was also used to filter out workloads with low parallelism and concurrency, since they did not fall in the scope of the suite. And finally, it was used to profile key metrics on concurrency and synchronization. In particular, these metrics were later used to demonstrate the higher diversity of renaissance with respect to other suites for the JVM. And all these analyses are described in more depth in the PLDI publication that you can see at the bottom of the slide. And in addition, P3 was also used to conduct large-scale analysis with NEB. And in particular, here, P3 was used to identify and then to analyze task parallel workloads. And again, you can find more details on this kind of analysis in the ECUP paper, in the ECUP publication, that again is written at the bottom of the slide. I would like now to present the evaluation of our profiling suite. As I mentioned before, the evaluation has been conducted on the Renaissance benchmark suite. And in particular, I will first present a preliminary analysis on the variability of the metrics in Renaissance. And then I will also focus on the profiling overhead. Regarding the evaluation settings, our evaluation considers only steady-state iterations, which means that we let the benchmarks warm up for many iterations until the garbage collector ergonomics and the dynamic compilation stabilizes. And we only activate the profiling after only in the steady-state iterations. We deployed the instrumentation and analysis servers on different NUMA nodes, and in particular, we made sure that Renaissance was running only on a separate NUMA node, not only from these two components, but also from every other application. And this was done mainly to reduce the measurement perturbation. And finally, for the same reason, we also made sure that during our evaluation, no other CPU, memory, or I/O-intensive application was in execution. Regarding metric variability, benchmarks are often used as reference workloads against which comparing the performance of other technologies. And for this reason, a good property of a benchmark is that a benchmark should exhibit a little variability over different iterations. They should be as stable as possible, in particular in steady-state iterations. So what we wanted to do here was to conduct a preliminary analysis on whether in multiple iterations the Renaissance benchmarks vary or not. Here, in particular, we focus on metrics that are related on parallelism, concurrency, and synchronization, since Renaissance has been developed in particular taking into account such metrics. Here, I would like to remark that our goal was not to conduct a full or a complete study on variability, but rather was to identify workloads showing symptoms of metric variability. And such workloads will be studied in more depth by future work. We profile all the metrics supported by P3 in 20 steady-state iterations. And in particular, for each metric, we compare the values in each iteration with the median across all the steady-state iterations, and we focus on benchmarks showing a variation of a plus minus 20% range with respect to the median in at least one iteration. Among the 25 benchmarks in Renaissance, we could identify a variation exceeding this range in 3 of them. The 3 benchmarks are reported in the slide, and they are in particular DB shoutout, that shows a high variation in the amount of acquisitions of implicit locks. The same metric also varies significantly in Neo4j analytics. And the third benchmark is movie length, where the amount of volatile accesses sometimes varies and differs from this 20% range. The table reports the relative value with respect to the mean of this metric in all the 20 steady-state iterations that we considered. Regarding DB shoutout, we can found in the slide that in 13 iterations out of 20, the amount of lock acquisitions is higher or lower than the 20% range. This can be seen by the red dots in the slide. Regarding Neo4j, we also find a variation from this range in some iterations, but this time the trend is different. In particular, here we can see a constantly increasing trend where the amount of lock acquisitions starts from a value of minus 25% with respect to the mean in the first iteration, and then constantly increases up to reach a value that is around 35% with respect to the mean. And finally, regarding movie length, while the amount of volatile accesses is rather stable and does not vary in most of the iteration, we can find that every 5 iterations there is a huge peak in this amount of volatile accesses. In particular, in the slide, the value has been cut because otherwise would have not been visible in the slide. But we can see that we are talking about values that exceed the median value by more than 300% in iterations number 5, 10, 15, and 20. So overall, while in the 25 benchmarks on Renaissance overall exhibit a low metric variability, in these 3 benchmarks, we found these patterns that indicate occasional or periodic operations that may introduce variability in workloads, and we are investigating why this is happening in these workloads. I would like also to focus briefly on the profiling overhead of our suite. The overhead was also measured on renaissance, and in particular, the table reports the median profiling overhead for every module across all the renaissance benchmarks. And again, this median was taking into account 20 steady-state iterations. So we can see that for most of the modules, the overhead is either lower or equal to a factor of 1.01. Here, the overhead factor is measured as the execution time of the applications when the instrumentation is active, divided by the execution time of the original application. There is an exception for free modules, in particular task, iLock, and volatile, where the profiling overhead is equal to a factor of 1.03. And this can be explained, so in the module called task, by the relative complexity in profiling the creation in particular and the execution of tasks. And regarding the modules iLock and volatile, we found that the Renaissance benchmarks make frequent use of implicit locks and also of the acquisition of volatile fields, which can explain the relatively higher overhead with respect to the other modules. And when all the modules are active, the total overhead is equal to a factor of 1.18. Before concluding, I would like to briefly describe the limitations of P3. So one limitation is that, unfortunately, the tool can over-profile some metrics, and this happens if the just-in-time compiler removes some events of interest without also removing the corresponding instrumentation code. Unfortunately, this is a well-known limitation of any profiler relying on bytecode instrumentation. There are ways to alleviate this problem, and we are now implementing or better integrating these ways to try to lower this limitation, at least for some metrics. Another limitation is that, unfortunately, the overhead is still significant for some applications when all the modules are active. So we found that in the practice, activating all the modules is often not needed. And on the other hand, the profiling overhead of individual modules is low. Anyways, we are looking into ways to further decrease this profiling overhead, in particular when all the modules are active. So to conclude, here I presented P3, which is a new profiler suite for concurrent applications on the Java virtual machine. Our tool can collect many kinds of metrics related to parallelism, concurrency, and synchronization. It incurs a moderate profiling overhead. It is readily applicable to prevalent benchmark suites, in particular Renaissance, Dacapo, Scalabench, and SpecJVM 2008. It is suitable for large-scale analysis with NEB, and it has also been very important in conducting previous research. Overall, we are confident that our tool can help researchers conduct novel analysis and better understand multi-threaded applications. As part of our future work, we are looking into new ways to further increase the profiling accuracy while also decreasing the profiling overhead. And we are also looking into expanding the set of metrics profiled by Pcube, for example, by integrating metrics that can describe the computations done by parallel streams. If you want to download Pcube, you can do so at the link that you can find in the slide. And you can, of course, feel free to contact me in case of need, in case of assistance in using the tool. That's all for my talk. I would like to thank you very much for your attention, and I will be happy to take your questions.
Any questions? Yes, please.
Yeah, hi.
Hi.
Hey. So you demonstrated the tool mostly for analyzing workloads, but have you also used it to find performance problems in specific applications?
So what we did, so this tool basically was an evolution of existing tools. So at some point, we had different tools that we put together, and this resulted in a part of this tool that was later expanded. So let's say the original components of these tools were used to locate performance problems. Yes.
Great. Follow-up question. Do you have any kind of ideas how one could kind of more automatically pinpoint performance problems based on the kind of metrics you provide?
So definitely we could, so it depends on, let's say, what is the long-term goal. So something that comes to mind is that one can have, for example, a reference value for a given metric. And if this value, let's say, significantly varies with respect to this reference, then we can pinpoint some performance problem. So we try to do that, in particular, taking into account the normalization that is provided by the bytecode count. And we identified somehow variation, let's say, benchmarks where this value was particularly high or particularly lower with respect to a value that we were expecting. So far, this was used mainly to locate, let's say, interesting workloads, like, for example, in renaissance, not yet to identify performance problems. But if I were to identify a performance problem, I would start by using a similar method.
Great. Thanks.
Any more questions? Okay, thank you.
Thank you.